Okay, now we're on. So I have to say my stuff over again, huh? Okay, okay. So I didn't get through all the domain and period type of material related to the other trig functions in the last segment, but you can go back to the recordings number 4 and 5 to look in more detail about that. The graphs of these 6 trig functions, here's sine and cosine in our textbook section 6.4 on the recordings number 6 and 7. Dealing with amplitude and period on sine and cosine. And then 6.5 handles the graphics of the other 4 trig functions. (6.5), page 411, I believe. And these are recordings number 7 and 8. And these are going to be your tangent, cotangent, secant, cosecant graphs. So, real quickly, I'm not going to spend a whole lot of time on this. Well, I'll spend a few minutes because this also is going to involve some distortions of the graphs as well, the transformations. So, and not all of their detail. But in a nutshell, we all know the sine function. There's one cycle of it. Here's another cycle of the sine function. That's our favorite one. And we know you can see its range from 1 as low as -1 there. And you can see its domain is all real numbers. It just keeps on going. Okay. Separately, if we would, and I'm going to go ahead and put a little label here, that's your sine of x as a function of x. Okay? Here is your cosine function that we're also familiar with, and I'm going to set my scaling up to line up with the graphs above. And so our cosine graph, we know, is going to look like this through a cycle, continues on. Similarly, domain moving off to the left, looking something like that. And we can label that one as our cosine of x related as a function of x. Right? We're all good at that. What we could then do is we could lay the reciprocal functions on top of these, and reciprocals of 1 we know are 1, reciprocals of zeros are undefined. 1 over 0 is undefined. So those are going to become vertical asymptotes when you start thinking about the reciprocal functions laid on here. Similarly, down here, 1's reciprocal on cosine, the reciprocal of 1 is still 1. The reciprocal of 0 is undefined, so we're going to end up with asymptotes for the reciprocal functions there. And we know that the reciprocal of sine is which function? Cosecant. Cosecant. Reciprocal of sine is cosecant. So reciprocals of numbers, look at this right here with my fingers. Reciprocals of numbers between 0 and 1 in value are going to be bigger than 1. And so you're going to get graphs that are up in here. And so I'm going to draw it in solid lines. There's a wing, or one portion of a cosecant graph. One part of it. And then there's another part, when you take reciprocals of negative numbers, they stay negative, and they have similar behavior to what you see here. And so here's a picture then of a complete cycle of a cosecant graph. Now, something you should keep in mind, at least with textbook problems. We know that if we were here at 30 degrees, we know that our sine reading is precisely 1/2. the cosecant at 30 degrees is then going to be precisely the reciprocal of that 1/2 is 2. So if you see a familiar number like 2 and you're dealing with a cosecant function, you can probably be assured that it's going to relate to 30 degrees, or look over here at 150 degrees. Your sine reading is a 1/2 as well, and its reciprocal likewise is then a 2. Okay, so the way that I've said this before is that the cosecant graph, think of it as just taking a ride on your sine graph. And I almost always, if I'm trying to draw a complicated cosecant function, I almost always will turn the problem into a sine function and draw it as a complicated sine function, and then I'll just let the cosecant take a ride on it. Is that all right with everyone? Okay. Similarly, down here with our cosine function, we can let the cosine function take a ride, let the secant function then take a ride on the cosine function. So we have our cosine graph dotted there. Here is our secant graph of x, shown right here. One wing of it, and here's another branch of it down here. And they have multiple periodic type of character on periods of 2 pi. All 4 of those trig functions you see here. Other things you can observe is that the sine function you know is odd. That's a property. Sine function's odd. So is its reciprocal. Look down here. The secant function has y-axis symmetry to the left and right of the y-axis. It has symmetry. And so therefore this thing is an even function. And both the cosine function and its reciprocal, the secant function, are then even. Okay. The sine function has an amplitude. The elementary sine function, sine x, has an amplitude of 1 and a period of 2 pi. So amplitude equals 1, the period is 2 pi. Same thing on cosine. The cosine as well has that same amplitude and period. Okay. Any questions? Let's now look at when we transform these things. And did I decide to do anything fancy on that? Let's do something like this. Let's say I had y equals the cosine, let's say 5. I'm going to keep it relatively simple because there's actually a separation in another section of the book where it gets a little more involved. But let's say I have a -5 cosine of 3 theta. Plus 2. Transformations. So what we always want to do is we always want to think, I presented this in several ways. One way I presented this was the following. Notice that outside the cosine function is this multiplier of -5, and on the tail end the addition of 2. If I move those away from the cosine and move them over here to tie them onto y, you can think of this as y subtracting 2 and then divide both sides by -5. Inside here, the cosine could be thought of as theta inside there for your angle divided by the reciprocal of 3, which is 1/3. This is one way I presented it. What's powerful about this for when you move into calculus is that the behavior of the transformation that's occurred from the original y equals cosine theta to get you to this thing is sitting right here. The behavior is similar in transforming from this old to this new. is sitting right here, and the behavior inside here is the transformation that's occurred to the old angle, becoming this new relationship here. If you do the math on this, you will see what the transforms are from the elementary graph that I have back here on this other board. This old y is being replaced with this whole thing that involves a new y minus 2 over negative 5. Now solve that for the new y. The new y reading is going to be negative 5 times the old y values. And then I'm going to move the 2, add the 2 to both sides, so it's going to be a plus 2. Similarly, on theta, the old theta down here is being replaced with theta over 1/3. This is a new theta now here. And so then if you multiply both sides by 1/3, you can see that the new theta is going to be 1/3 times the old theta readings. That's one way of describing the transformations. What I like to do, you can come back up here once you get good at this, you can come back up here and see this. What this does is it takes the old y's and it multiplies them by minus 5, which is going to do what to the picture of your basic cosine? What does just the negative 5 do to the old y readings? It makes them become negative where they were positive, and it makes the positives that were, it makes the negatives become positive, and it makes the positive old values negative, doesn't it? So it turns it upside down. So when I see this sitting on a trig function, I just think of the graph doing that, flipping it upside down. The 5 is an amplifier. You're going to be multiplying the old y readings by 5. So that's a stretch, a vertical stretch by a multiple of 5. Inside here on theta, we're making the old theta readings, the old angle readings on the cosine graph 1/3 as much. So we've applied a squeeze to the graph. So even though it looks weird here, right here you notice that that 1/3 is smaller than 1, and that acts as a squeeze factor, like an accordion, changing the period of the function. And so when you see it in here like this, try to think of it in terms of its reciprocal, and it's acting as a squeeze factor to change the period. And then lastly is on the y, you're adding 2 to the, after you've multiplied the old y's by 5 negative, you add 2, that's going to cause the whole graph to get lifted up by an amount 2. And we've gone over this numerous times. It never hurts to review it though, because it's a tough spot for people. Any questions on that? There is another way of presenting that. Actually, there's multiple ways of presenting that. Another way of presenting this is to come in here and, well, probably just looking at this and realizing that that's going to cause it to become negative times 5 and then up 2. But another way of presenting this material inside here on the independent variable is to take that angle, that whole thing as an angle, and you know it's equal to, at a starting point, at a start of a cycle, you know that 3 times this angle, I'm going to put a little subscript s here to mean start, you know that a cosine function, elementary cosine function, starts at 0 degrees on a cycle. You could start anywhere, but you can think of it this way to help you get the graphing going. And then you solve that for the starting value, and that remains the same, still 0 degrees when you divide both sides by 3. It ends its cycle by taking the whole angle, ends the cycle when you know the fundamental function ends the cycle at 2 pi. You then solve that, and this will tell you the ending spot. So then to draw your graph, what you can then do is you can say, okay, I know I'm going to have an amplified cosine wave upside down, lifted up by 2. So what I do is I go up 2, I draw my axis, and then do what?
Go to -3.
Excuse me?
Start at -3.
Okay, so I want to go 5 below the axis because you, as you just said, this thing has been turned upside down. And so normally it would start up on a crest at 1, but we've made it 5 times as much and turned it upside down. So it's actually going to start down here.
Put a tick mark at 2/3 for your
Yeah,
entire...
yeah, and then actually what I'm going to do then is I'm just going to come out here, as you just said, and I'm going to come out here and lay in where this thing ends the cycle. And then I'm going to cut that in half, which is pi/3. And then I'm going to cut that in half again, and that becomes pi/6. And that's going to be the places where we are going to see nodes occurring on the axis here. So the graph then is going to, and it's going to finish its cycle at 2pi/3 back down on a trough. Halfway through, we should expect to see it up on a crest, up at 7. Two plus 5. And then back on a node at 1pi/6, 2pi/6, 3pi/6. Think about that. 3pi/6 is pi/2. And it's going to be back on a node there and then back down on a trough. So I can then draw a cycle of that. There it sits. You also know that for these things that happen to be called sinusoids, sine or cosine functions, they have a period. Sinusoids will always have a period of 2pi/omega if you're dealing with some model like this or this. They will always have periods of 2pi/omega if you wish to memorize a formula. Okay. Another question that comes up a little later in a course could be taking this original function and setting it equal to some value. What if I said equal to 4? What if I said, and this comes up later, -5 cosine 3 theta plus 2 equals 4. Solve. That's a trigonometric equation, very important type of an equation. And so that thing is solvable. How does it show up here on the graph? Because you folks had some trouble with this, I think I've seen on quizzes and tests before, this kind of a thing. How does it show up here graphically? Help me. Yeah. Isn't this a y value here, folks? Just like Deanna said, when this y value becomes 4 on the picture here, 1, 2, 3, 4, we're talking about the intersection of the function at y = 4. It's not that tough. Graphically, it's easy. And you're going to end up with an answer a little bit past pi/6 here. There's one answer right there. I'll label it A. And there's going to be another symmetric one to pi/3 to either side of pi/3 right over here. There's another answer right there. And you can turn trace on or intersect features of your calculator and pin that point down. Okay? If I remember, when we get to the, in our review, when I get to solving equations, which comes up later in the course, later in this review, in 7.7 and 7.8 in our book on tape or recordings number 15, I believe, we go into the discussion about solving equations like that. All right? So let me hold off on going into the details there. What if this original problem here instead did not have cosine? If it had secant sitting right there? Instead, what would you do? to draw it?
Just draw the cosine and then the
Thank you.
secant rides off the cosine.
Good, you were listening to what I said earlier. You draw the cosine function and then just let the secant take a ride on it. Now, you want to be a little bit careful about that on where your asymptotes sit. But just leave it at that. That's not a particularly, we don't need to go into depth on that. But just be careful when you do the work and then double check yourself with your technology using a calculator on it. Okay? All right. Let's go back. Let's go on now to, oh, and let's see, I did do, on the graphs here in 6.5, I did handle the layout and the connection between sine and cosine and the cosecant and the secant. So we took care of that, but I hadn't yet said anything about the tangent and cotangent graphs. So let me just do that real quickly with you, and then we'll end this segment. Several ways you can think of your tangent function. You can draw a graph, as I did over here, of sine and cosine, and you can imagine taking the readings off of those and dividing the sine readings by the cosine readings at a particular angle. You can see there's going to be trouble when you divide by cosines where cosine values are 0. So you would expect to see then asymptotes showing up on this tangents graph because of it being the ratio of sine of an angle over the cosine of an angle. You're going to expect to see vertical asymptotes showing up periodically wherever cosine takes on a 0 value. And you know that occurs at pi over 2 and every period thereafter, every pi. There's one of them, and there are multiple ones, an infinite number of them. You graphically also can see that if you take positive values in this first region from 0 to 90 degrees here, if you take these positive readings and divide them by positive readings, you're going to end up with positive tangent values. If you go beyond that, past 90 degrees, you're going to see positive values divided by negative values, which yield negative results. So without going into too much more detail, you can go back and look at the other recordings on this in detail. Here is one wing of a tangent, and another one looks like this. Is this an x cubed function, like in algebra? What makes this distinctly different from an x cubed function? Vertical asymptotes. This thing essentially has sidewalls on it, and you can't, it's not if those asymptotes are there, it's definitely not going to be a cubic. Okay, looks like that. And what's an important value? Well, here's an important value to keep in mind. This spot right here, 0, 0. Keep track of that. And another one is over here at pi over 4. If you're at pi over 4, this height is 1. That's the tangent of 45 degrees, or pi over 4 is 1. And you want to keep tabs of that if you're transforming this thing. Like if you were trying to draw something like 3 tangent of x, then you'd be having a vertical stretch by a factor of 3. Okay. And then, of course, you can come in here and change the period. And keep in mind that the period of tangent, remember, is in its fundamental form is pi. And so a formula for handling y equals the tangent of omega x is not going to be a 2 pi over omega. It would have to be, the period would have to be pi, the fundamental period, divided by the omega. And in 10 seconds, The cotangent graph is the reciprocal of this thing. Now, I actually will probably make a recording about functions and their reciprocals. That's a whole topic area in itself that I haven't had time to talk about. Very important and useful to you as you continue on. In a nutshell, positive values in the reciprocal are still positive. 1 stays 1. Zeros become undefined in the reciprocal, 1 over 0 then. Getting the idea? Increasing becomes decreasing. Vertical asymptotes in the reciprocal become, no, not inverses, become zeros. So anyway, you'll have to wait for that recording, okay? But anyway, the idea is this. What happens is 1 stays 1, the zeros become vertical asymptotes, vertical asymptotes become zeros, and you think your way on through that, and what happens is you get something that looks like this. This is pi over 2, and then when you get out here to pi, you've got this asymptote sitting there. So there's one cycle of your cotangent function. And they occur periodically. Same period if you're dealing with something like the cotangent of an omega x. Cotan omega x, period will be pi over omega. All right, let's go ahead and end this segment, and then we'll fire up the last one, and it will be a short one.